Hello everyone, I hope all of you are doing well. So today we're studying 15.2, which is double integral over general regions. In 15.1, we talked about double integration over rectangular regions. Rectangular regions we meant by when x is between two specific numbers and y is between other two specific numbers. So when we have got this one, it forms a rectangular base for the object. It forms a rectangular base for finding the volume of the object that's required from us. Here we are talking about double integral over general regions. So if the region is not a rectangular shape, how can we deal with it? How can we find the limits of integration, and how do we do the integrations? How do we evaluate the integrations? So here we are starting with Fubini's theorem. Let's see what is it stating, and later on we will see how we can find the limits of integration, going through examples and the steps that are given to us. Okay, so Fubini's theorem states that if we have got f of xy, which is continuous over the region that is given to us, and if x is between two specific numbers, but here y we have got is between two functions, not two numbers, as we have studied in 15.1. So if the order of integration is dy dx, here the integration with respect to y, the limits of it runs from g1 to g2, and the limits of integration for x runs from a to b. In another way, if the region is given to us in the second one, as the second one, where the limits of y are known, okay, known numbers, but limits of x are functions, so the limit of integration is written as dx dy. So the inner integral, we are writing the limits of integration for x, which is h1 and h2. And for the outer integral, we are writing the limits of y, which is c and d that is given to us. Okay, how do we find these limits of integration? Because not every time these functions are given to us. Of course, the regions are given to us, but sometimes you have to change the order of integration for finding, for evaluating the integrals that we have got. We will go through some steps that we can find the limits of integration, both for dx and for dy. Before going through the example, because it's not explained yet, I'm going through finding the limits of integration. So if the integral that we have got is dx dy, how do we find the limit of that dx, and how do we find the limit of that y? Or if the order of integration is dy dx, how do we find the limits of that integration? Of course, the region is given to us verbally. So if something like that is given to us, this example, or let me say these steps, are explained on that region. What is that region? This region is between the function x plus y that's equal to 1 and the function x squared plus y squared equal to 1. So this region is between those two functions that is given in here. If this is the case that we have got, and the order of integration is, let me write it here, the function here, and we have got dy by dx, what are the steps that we have to do? For finding dy by dx, we are using vertical cross section. Okay, what do we mean by using vertical cross section? Here we have got three steps to find the limits of integration when we have got dy and dx. The very first step that we have to do is to sketch the region that is given to us. It is very important when the region is given to us and you're sketching this graph of the base. Okay, so that is very important. Of course, in most of the cases, if you're not sketching this graph, the base, you cannot do the other steps, finding the limits of integration and evaluate the integral. Okay, to find this y limits, okay, here, to find the y limits, what are we going to do? We are drawing a vertical line, okay, like it is given in here. We are drawing that vertical line, and it passes through the region that is given to us. This vertical line enters the region from this point and leaves the region in that point. So this will be this point, this line, this function will be the lower bound for the dy, and this one will be the second function will be the upper limit for the integration of dy. So here, this function here, okay, the entering place, what is this function here? It is given to us, it is x plus y, that's equal to 1. Since we are finding the limit of integration for y, so we have to determine y is equal to what? So it becomes y equal to 1 minus x, and here we are writing y equal to 1 minus x, as it is given in here. Okay, then the function, the vertical cross section, the line that we have drawn, leaves the region in that function. What is that function? It is x squared plus y squared equal to 1. Okay, changing this function to y terms, it gives us this function. So here the upper limit of this one will be y equal to square root of 1 minus x squared, which is this one written here. Okay, so now we found the limits of integration for y, the inner integral. Now we want to find the limits of integration for x, okay, the outer integral. How do we find the limits of integration for that x? Okay, here when we see the region that we have got here, okay, on the x-axis, if you look at it, it runs from where to where? It is starting in that point and runs to 1. So the limit of that integration will be from 0 to 1, as it is shown in here. So that's how we find the limits of integration when the when the order of integration is dy dx. Now I'm moving to the case if the order of integration is dx, okay, and then dy. How do you find this order of integration? We are doing this nearly the same way that we did for the order of integration, that is dy dx, but instead of course, the first thing that we have to do is to sketch the graph of the region, and then instead of drawing a line vertically, we are drawing a line horizontally, okay, parallel to the x-axis and passing through the region that we have got. If we look, this line that we have drawn, it is entering the region in that point. What is that point? It's the function x plus y, that's equal to 1. So in x terms, this one is the line 1 minus y, which is written here. And then this line that we have drawn, it is leaving the region in that place. So it is this function x squared plus y squared, that's equal to 1. If we write this function in terms of x, it gives us this one. So we write the upper bound of the x as 1 minus y squared under the square root. Now we are done with the limits of x. We have to find the limit of y. Okay, how do you find the limit of integration of y? If you look at the region, okay, it is here, and you look at the y-axis, this region starts from here, okay, and it goes till here. So this is the limit of integration with respect to y. So that's why we have written 0 and 1 for the limits of integration for y. Of course, these things become clear. Here the steps are written. Okay, here it's talking about how to use the horizontal cross section. And of course, these steps, those things will be clear when we are doing an example, when we are evaluating an integral. So the example that we have got, the first example that we have got here, is it is requiring us to find the volume of a prism, okay, whose base, so the base of the object that we have got is given to us. The description is here. It's a triangle, so we know that the base that we have got is a triangle in the xy plane and bounded by the x-axis, the line y equal to x and x equal to 1. Okay, so let's do this one. We are going to draw this region and see how we will work on it. So here I've written the example here. Okay, so the lines that we have got is the x-axis, y equal to x and x equal to 1. Of course, this drawing this region is very easy for you. First you have to draw the xy coordinate, okay, and then we are drawing the bounds. The first one is the x-axis. This is the x-axis, so this is one of the bounds. And then the line y equal to x, the line y equal to x is this one, y equal to x, and then x equal to 1. X equal to 1, if we have got that this point is 1, for example, okay, and then here we have got 2, x equal to 1 is the line this one, x equal to 1. This point is what? This point is the x-axis equal to 1 and y-axis equal to 1, because this is the intersection of the line y equal to x and x equal to 1. So it gives us 1 and 1. This point is the origin 0, 0, and this point is the point 0 and 1. Here I have sketched the graph, okay, in a better way. Here I just wanted to show you how we draw the region that is given to us. Okay, first we want to integrate this function, finding this volume with respect to y first, okay, and then with respect to x. So what are we going to do? We are writing dy by dx. We have to find the limits of integration for y and then the limits of integration for x. For finding the limits of integration for y, what are we going to do? As we studied from the steps, we have to draw a vertical line, okay? We have to draw a vertical line, sorry. How do we draw that vertical line? This is the region that we have. It's passing through that region. Sorry, the line is not so much vertical. It enters the region in that point and leaves the region in that point. What is that point here? Here is the x-axis. Okay? Here is the x-axis. So it is entering this region for y from 0 and then leaves it at y equal to x, so I'm writing x here. That is the bounds for the y, dy I mean. And now we are looking at for bounds of the dx, the limit integrations, the limits of the integration, not the limit integrations, the limits of dx. How do we do that? The region that we have got is this part, okay? Where does that region start? It starts from 0, okay, and ends at 1. So it is from 0 to 1. Now we are doing the normal integration. Since we know the limits of integration, we are taking the integrals normally as we have known previously. And then simply we get the value of the integral. Of course, as we have studied previously, to take this integral, to evaluate this integral, first we are doing the inner integration, by this part, Okay, and then when we are done with dy, then we are dealing with the dx. So here I will have the integration, start evaluating it from 0 to 1. This one changes to 3y minus xy minus y squared over 2, and the integral runs from 0 to x, and here we have got dx. This one, when we input x into this integration and 0, we get that this simplifies to from 0 to 1, and this becomes 3x minus 3x squared over 2 dx. Now we have got a simple form, okay? And then this one, we are taking the integration with respect to x. So this one changes to what? It changed to 3x squared over 2 minus x to the power of 3 over 2. And the integral, the limit runs from 0 to 1. Putting 0 and 1 into that integral, it gives us the value equal to 1, which is the required volume for that prism that we have got with the base in triangular form. Let me draw this one again. Okay, that was what finding the volume of that prism when the order of integration is dy dx. Okay, how about if we have got the order of integration? For example, somebody else wants to find the volume of this integration using the order dx dy. Okay, so using the order dx dy, we have to do what? We have to draw a line, okay, a horizontal line that passes through the region, and it enters the region from y equal to x and leaves the region from x equal to 1. Okay, so here what do we get? Here the limits of this integration, it becomes, instead of writing y, but here we have to write x in terms of y. So here I'm writing y because it enters the region in that point. Here x is equal to y, that's why we are writing this bound as y. Where does it leave the region? From x equal to 1, so here I'm writing the 1 here. Now we are looking at the y, limits of y, okay, limits of integration for y. Again, the region that we have got is this part, okay. This part is what? Starting from y equal to 0 to where? To here, okay. This is 1 for y-axis, so the limits of integration for y, it is 0 and 1. Okay. Now, since we found the limits of integration, of course, taking the integral is very easy. Okay, we are dealing with the inner integral first, and then with the outer integral. So here we will have from 0 to 1, the integral changes to 3x minus x squared over 2 minus xy, running from y to 1 dy. Inputting y and 1 into this function 3x minus x squared over 2 minus xy, it gives us the result as of course this one is from 0 to 1. It gives us 3, or let me say 5 over 2, okay, minus 4y plus 3 over 2 y squared, and that is dy. Taking that integral with respect to y, it gives us 5 over 2y minus 2y squared plus y to the power of 3 over 2. And this runs from 0 to 1. Substituting 0 and 1 into that function again gives us the value equal to 1. Okay, so that's how we are finding the volume of an object using the order either dy dx or dx dy, given the steps that we have studied in the previously in that section. Okay, so now we are moving to example 2, which requires us to calculate this double integration that is given in here. It is given in general form. It says over the region that is given to you, which is the triangle XY, in the xy plane bounded by the x-axis, y equal to x and x equal to 1. So the base of this object that we have got here is the same base as we had in the first example. Here it is written as dA, so we are free whether we are using dx dy or dy dx. Okay, let's move to see how to solve this double integration. If we use the case dx dy, solving this integration will be hard. So we are changing the order of integration. Instead of dx dy, I'm starting with dy dx. Why? Because dy dx, when it is dy, first we are taking the integral with respect to y. This function that we have got, sine x over x, will be all considered as a constant. So dealing with that as a constant will be easier for us. So first we have to find the limits of integration for y and then for x. Okay, so finding the limits of integration first for y, we have to draw a vertical line that is going through the region that we have got and see where it enters, where it ends. So if you look at this one, it enters again from here where it gives us 0, y equal to 0, and it leaves the region in that point in which the function here y is equal to x. So the bounds for that function, for that dy, the limits of integration are from 0 to x, as we have seen in the previous example. For finding the limits of integration for the dx, okay, we said we are considering the region where it starts on the x-axis and where it ends. So if you look at that region that we have got here, it's starting from here, from 0, and it ends here. So the bounds that we have got is from 0 to 1 for the x-axis. Again, what are we going to do? We are going to solve the inner integral. It gives us what? From 0 to 1. Sine x over x is all considered as a constant, so we will have y multiplied to the constant that we have got when we are taking the integral with respect to y. And this runs from 0 to x. Then dx is remaining unchanged. This integration changes to what? From 0 to 1. Then this one will become, if we put x and 0 into here, this function will change to what? It will be x sine x over x minus 0 multiplied to sine x over x. So this part all vanished, is 0. This x and x cancel each other. The only thing that will be left here is sine of x, okay, with the dx. So now if you look, the integration is easy to be evaluated. Integral of sine x, of course, is equal to what? Is equal to minus cosine of x, and the integral runs from 0 to 1. Putting these values into this function gives us a result that you can find it yourself. Okay, so you're putting it minus cosine of 1. Of course, you must have a calculator here for cosine 1. and then putting 0 instead of the x, and gives you the value, which is given in your course material, that is approximately equal to 0.46. This is the value for that integration. Of course, solving this integration with respect to dx dy, if we change the order of integration, we run into a problem that sine x over x cannot be solved easily when the order of integration is dx dy. So that is all about example 2. We will be moving to example 3. Okay, so now we have got example 3. Example 3 doesn't require us to find, to evaluate this limit that we have got, I mean this integral that we have got. The integral with its limits is given to us. Okay, it says sketch the region. So here the limits are given to us, and it says sketch the region of the integration, and then write an equivalent integral with the order of integration reversed. Here the integration is given to us as dy dx. It's required from us to change that order of integration with the same function to dx dy. Okay, so let's see how can we do that. Of course, first, when it says sketch the region that is given to us, if you look at here, these limitations are given to us, the limits of integration. Since the inner one is for the y-axis, so this one we know that this is y equal to x squared, and this is y is equal to 2x. Okay, and the outer integral, since it is for x, so we know that x runs from 0 to 2. Okay, now we are coming to sketch the graph of these integrals that we have got. What do we have to sketch? We have to sketch y equal to x squared and y equal to 2x. X squared, as you know, the graph of it is like that. Let me a little bit make it open. Okay, the graph of it is like that. And the graph of 2x, you know, it's the graph of it is x, a little bit sloping up. So the graph of y equal to 2x is something like that. So here we have got y equal to 2x, and here we have got y is equal to x squared. This is the region that we have got here. Okay. We know that x-axis runs from what? X-axis runs from 0 to 2. So here is the 0, and here is the 2. What is that point that we have got here? This one is 2. We know that x-axis is 2. Okay. And y-axis is equal to 4. Why? Because y is equal to 2x. When you're putting 2 into y equal to 2x, it gives us 4. Or you can use the other function. You say y is equal to x squared. So putting 2 into the x squared gives us 4. So this point is 2 and 4. Here I have sketched the graph on the left-hand side in a better way. Now we are coming to change the order of integration. Okay, to change the order of integration, let me do this one again. Okay, to change the order of integration, we have to change the inner one to dx, okay, to order of dx, and the other one dy. How can we do that? We know that for finding the limits of integration when it is dx, we have to draw a horizontal line that is parallel to the x-axis and passing through the region that we have got. It enters the region in that point. Okay, here if you look from this graph, okay, it is entering from this point and leaves in that point. Okay, what is that point that we have got here? Here we have got y is equal to 2x. So x is equal to what? X is equal to y over 2. So here we get the first bound is equal to x y over 2. Where does it live? It leaves the function at that point. What is this function? This function is y equal to x squared. So x is equal to what? It's equal to square root of y. We know that x is equal to plus or minus square root of y, but in the first quadrant we only have got square root of y. So here the bound is x equal to square root of y. Now we are looking at the bounds of y. Okay, how do you calculate the bound of y? The limits of integration for y. We said we are looking at the region that we have got from where does it start on the y-axis and where does it end. If you look, it starts from here, okay, and ends here. So the limit of integration will be y equal to 0 to y equal to 4. And this is what is required from us. It is only changing the limit of the integration, the order of integration, where it is given to us as dy dx, and we have to change it to dx dy without solving this integration. That's all for that example. We are moving to what? Properties of double integration. Okay, for properties of double integration, it is the same thing as we have studied in the single integration. What does it say? The first one, of course, we have got f of x and g of x are continuous functions on the bounded region that we're finding the integral on. The first property is the constant multiple rule. When we have got a constant multiplied with c, as we know from integration, the constant can be written outside the integrals, and then evaluate the double integration of the function that we have got over either dx dy or dy dx. Sum and difference, when we have got two functions added or subtracted from each other over a specific region, this double integration is distributed over this one and that one, over f of x and g of x. So we can find the integration as double integral of f of xy plus or minus double integral of g of xy. So double integration, as we have studied in single integration, is distributive over addition and subtraction. The domination, the third one, we have got what? It says if we find the double integral of a function and it is greater than 0, so for we know that from this one, we know that f of xy is greater than or equal to 0. So, or let me say in other words, if the function that we have got is greater than 0, that means if it is a positive function, that means its values, its outputs are positive, for sure we will get that its double integral as a positive value. The second domination, it says what? It says if we have got a function that is greater than or equal to another function, that means the output of this function is, all of the outputs of this function at specific points are greater than or equal to this function, then for sure the double integration of f of x, its result will be greater than the result of the double integration of g of xy. The fourth one, we have got additivity. Additivity is that, let me say, when you can separate the regions into two different regions. Here we have got, if you have got double integration of f of xy, this can be simply distributed over two regions. Yani the region that we have originally, we can change it to R1 plus R2. For example, if this is the region that we have got, and the integration is found over that region, we can make it as R1, finding the integral over that region, and plus finding the integral of that region. It will give you the same result as finding the double integral over the specified region. Well, this thingy, this property, depends when will we need it and how can we use it throughout the examples that will be given to us. For example, in example 4, we have got a case similar to what we have got in additivity, but I will leave example 4 for another video. So have a nice time, and I hope you will understand. Have a good time.